Why did medieval iron objects survive centuries with minimal corrosion while modern steel tools and structures often show visible rust within only a few years? This question might sound simple at first, maybe even like a matter of myth versus reality, but when we look at the physical artifacts that historians and archaeologists have uncovered across Europe, the Middle East, and Asia, we begin to see a consistent pattern that challenges our assumptions about ancient craftsmanship. Many surviving medieval hinges, nails, tools, and structural components show a surprising level of resistance to rust. Their surfaces, although aged and darkened, remain intact, coherent, and structurally strong. It is a direct contradiction to modern expectations because people assume old methods must be inferior simply because they were created without industrial machinery or precise metallurgical knowledge. Yet the evidence suggests medieval blacksmiths unintentionally developed a multi-layered anti-corrosion technique through slow and careful manual work. They worked iron by repeatedly heating and hammering it, a process that removed pockets of air and burned away many impurities that modern mass-produced steel often still contains. Every hammer strike compacted the metal structure further, helping to eliminate micro fissures that usually act as starting points for future corrosion. This wasn't something they understood scientifically, it was simply the result of traditional craftsmanship evolving over generations, but that's only the foundation of the phenomenon. The real breakthrough comes from the surface chemistry created during their heating, cooling, and quenching processes. When iron is heated just below its melting point and cooled slowly in open air, it forms a black oxide layer known as magnetite. Unlike the red rust that flakes, expands, and weakens the metal, magnetite is stable, dense, and actually protects the iron underneath. This dark, almost ceramic-like layer acts as a natural shield against oxygen and moisture. And when medieval smiths quenched the hot metal in oils, animal fats, fish oil, linseed oil, or plant oils, the extreme heat transformed the oil into a thin carbonized coating. This coating bonded to the magnetite layer, creating a double barrier that repelled water and locked out corrosive oxygen. Modern engineers call this carbonized film a polymerized organic layer, but medieval craftsmen simply observed that tools quenched in oil lasted longer. The combination of carburization, black oxide formation, and oil quenching produced iron that could withstand centuries of exposure. Modern steel, however, is designed for speed and cost efficiency, not longevity. Factories rely on rapid heating cycles, high-temperature processing, recycled materials, and alloy adjustments, often resulting in pores, inconsistencies, and internal stresses that medieval iron avoided. The very processes that allow us to produce millions of tons of steel cheaply and quickly also reduce the metal's natural durability. Industrialization replaced slow craftsmanship with fast mechanization, and in doing so, we lost a deep, experiential knowledge of how to create exceptionally long-lasting surfaces. Medieval craftsmen worked with patience, intuition, and repeated observation. They weren't chasing efficiency, they were simply trying to make the strongest tools possible with the materials they had. Ironically, the modern world, despite its technology, often produces inferior durability in everyday objects. When archaeologists compare modern untreated steel nails with medieval oil-quenched nails, the differences are striking. Modern nails degrade within a year or two in outdoor environments, while medieval nails can survive centuries embedded in wood or soil. The forgotten methods that blacksmiths once relied on reflect a level of craftsmanship that industrial processes have largely eliminated. The loss wasn't accidental, it was a deliberate trade-off to meet demand and scale during the Industrial Revolution. Yet today, as researchers attempt to reproduce these ancient techniques, they discover that medieval metals, created slowly and manually, sometimes outperform modern metals made with advanced machinery. This makes us question what progress truly means. Perhaps it is not always about speed, volume, or technological complexity. Sometimes, the old ways didn't just work, they worked better, and the proof is still surviving in archaeological sites, museum collections, and centuries-old buildings that continue to defy corrosion even today. How exactly did such knowledge disappear, and why did societies that greatly valued durability shift toward methods that produce metal far more vulnerable to the environment? The answer lies in the sweeping transformations that occurred during industrialization. As economies expanded, the demand for iron and steel skyrocketed. Instead of a few blacksmiths producing specialized tools, entire industries needed to manufacture enormous quantities of metal quickly and cheaply. Slow carburization, careful hammering, oxygen-controlled heating, and oil quenching over long periods were impossible to implement on massive factory scales without slowing production dramatically. Every step that medieval craftsmen performed by hand required time, observation, and deliberate adjustment. factories replaced this with standardized, high-temperature furnaces that melted large batches of metal together. This created uniformity, but also introduced impurities and inconsistencies. While the new metals were good enough for industrial needs, they lacked the accidental advantages that ancient craftsmanship produced. Additionally, many ancient techniques were passed orally from master to apprentice rather than written down. When industrial processes replaced manual blacksmithing, entire lines of knowledge vanished within a generation. What once was common knowledge, like the ideal color of iron before quenching, the smell of properly heated metal, the sound of a hammer strike indicating internal density, became irrelevant in the world of mechanization. The irony is that modern material scientists now analyze the very objects medieval craftsmen left behind to understand how they achieved such impressive corrosion resistance. Using advanced microscopes, they have discovered layers of carburized steel, magnetite, and carbonized oils blending together into a hybrid structure that is difficult to replicate artificially without extremely controlled environments. Yet medieval artisans achieved this with nothing more than charcoal fires, simple bellows, and generations of practiced intuition. Some enthusiasts today attempt to recreate these lost methods in small-scale workshops. When they follow the medieval processes faithfully, slow heating cycles, charcoal exposure, long oil quenches, and gradual cooling, the results consistently show higher corrosion resistance than untreated industrial steel. These modern experiments confirm what the archaeological evidence suggests: medieval craftsmen accidentally stumbled upon a naturally superior technique. This raises an important point about human knowledge. Not all progress is linear. Sometimes, societies forget techniques that were more effective simply because they were not compatible with mass production or fast economic growth. We tend to assume the present is always more advanced than the past, but the surviving medieval ironwork challenges this narrative. It shows that knowledge can be lost when practicality outweighs refinement, and so the real story is not just about chemistry or material science. It is about the value of craftsmanship and the consequences of prioritizing quantity over quality. The medieval anti-rust method represents a form of progress that modern industry abandoned. Yet, with environmental challenges and sustainability concerns rising today, some engineers are reconsidering the benefit of slow, nature-based processes. The medieval technique, simple yet effective, may prove useful again in applications where long-term durability is more important than rapid mass production. After all, medieval blacksmiths weren't trying to meet global market demand. They were trying to make something that would last a lifetime, and as their surviving iron objects prove, many of them succeeded beyond anything they could have imagined. Why did medieval iron endure for centuries in certain regions while modern metal structures corrode rapidly under similar conditions? The answer involves not only blacksmithing techniques but also the unique environmental context in which medieval people lived. Unlike today, medieval towns and villages were built with little exposure to industrial pollutants, sulfur compounds, and acidic rain, all major accelerators of corrosion in modern environments. The atmosphere was cleaner, the soil less contaminated, and the humidity patterns more stable. When researchers examine metal objects preserved in medieval wooden beams, shipwrecks, and stone walls, they often find that the environment itself acted as a stabilizing force. Medieval homes were insulated with natural materials like clay, straw, and timber, all of which absorbed moisture and reduced rapid temperature fluctuations. This kind of natural climate buffering helped iron avoid the constant cycles of condensation and evaporation that typically trigger rust. In other words, the medieval world unintentionally protected its own metalwork through the organic simplicity of everyday life. Another overlooked factor is how medieval architecture interacted with the metals embedded within it. Iron nails, clamps, and hinges were often surrounded by dense hardwoods, lime plaster, or stone materials that created microenvironments with low oxygen exposure. When oxygen access is restricted, rust formation dramatically slows. Modern construction, by contrast, frequently leaves metal components exposed to open air, moisture, and temperature swings. Medieval builders didn't design structures with corrosion science in mind, yet their preference for thick, natural building materials produced ideal conditions for long-term preservation. Even the placement of metal objects mattered. Archaeologists note that many medieval iron components were installed in parts of buildings that rarely saw direct water exposure, reducing the likelihood of oxidation. These combined factors created a passive yet powerful protection system around medieval iron. Soil chemistry also played a significant role. Many medieval artifacts recovered from agricultural areas show better preservation than expected, largely due to the alkaline or mineral-rich soils in which they were buried. Acidic soil accelerates rust, while alkaline soil slows it considerably. Medieval farming relied heavily on natural fertilizers, wood ash, lime, and animal waste, which raised soil pH and unintentionally created corrosion-resistant environments. Modern agriculture, however, uses chemical fertilizers and pesticides that often create acidic or corrosive soil conditions. When iron tools or structures come into contact with these environments, they degrade significantly faster. This difference in soil chemistry, shaped by centuries of agricultural practice, helps explain why medieval objects sometimes survive intact while modern equivalents disintegrate quickly. Even water quality contributed to iron preservation. Medieval people sourced water from rivers, wells, and springs rather than chlorinated or treated water. Modern water often contains chemical additives that increase corrosive activity when metals are exposed repeatedly. Medieval well water, in contrast, typically contained higher mineral content that produced a thin protective scale on metal surfaces. This mineral layer, similar to hard water buildup in pipes, acted as a barrier against corrosion. While medieval people had no scientific understanding of it, the practical result was metal tools and chains that lasted through generations of use without significant rusting. In harsh environments like coastal regions, the same principles applied. Salt crystallized on iron surfaces, creating a dry barrier that limited moisture contact except during storms. When all these environmental elements are combined, clean air, natural construction materials, mineral-rich water, alkaline soil, and limited chemical exposure, they form a clear picture. Medieval life created conditions under which iron naturally survived far longer than it does today. The durability of medieval iron wasn't only due to craftsmanship, it was the result of an entire world that did not attack metal the way the modern world does. Pollution, chemical treatments, acid rain, synthetic building materials, and industrial byproducts all contribute to the rapid corrosion we consider normal. But what we see in medieval artifacts proves that rust is not simply a matter of time, it is a matter of environment, and medieval environments, unintentionally but consistently, preserve the iron of their era better than many modern conditions preserve ours. This understanding adds a deeper dimension to the mystery of medieval iron longevity. It wasn't just how they forged it, but where it lived. Another important yet frequently ignored influence on medieval iron preservation is the slower pace of material degradation caused by limited mechanical stress. Modern metal is constantly exposed to vibration, friction, and mechanical fatigue from vehicles, machines, and urban infrastructure. These repetitive stresses produce micro-cracks that allow moisture to penetrate deep into the metal, accelerating corrosion from the inside out. Medieval objects rarely faced such extreme mechanical environments. Tools were used at human speed, buildings experienced minimal vibration, and weapons were not subjected to industrial scale loads. As a result, the absence of mechanical fatigue helped many iron artifacts retain structural integrity for centuries. What this tells us is that corrosion is not just chemical, it's also physical. The medieval world naturally avoided many of the forces that make modern metal deteriorate so rapidly. Even storage and daily handling routines in medieval society contributed to iron longevity. Most tools and weapons were kept indoors, often near hearths or in dry storage rooms that absorbed humidity. Medieval homes constructed from timber, clay, and stone maintained relatively stable indoor temperatures. Today's metal objects, on the other hand, are frequently left in garages, basements, balconies, or industrial environments that fluctuate between cold nights and hot days. These sharp thermal transitions cause condensation, which is one of the primary drivers of rust. Medieval storage patterns unintentionally minimized temperature swings and condensation cycles. In fact, some old workshops were so well insulated by natural materials that their microclimates remained nearly constant year-round. This created ideal preservation conditions without any deliberate effort. The final environmental factor worth noting is the absence of airborne salts and industrial contaminants in medieval air. Modern cities produce countless microscopic particles, carbon soot, sulfur dioxide, nitrogen oxides, chemical vapors that settle on metal surfaces and form acidic films when exposed to moisture. These films attack iron aggressively, dissolving protective layers and accelerating rust formation. Medieval air, even in densely populated towns, lacked the industrial pollutants that dominate modern atmospheres. The worst contaminants came from wood fires or simple kilns, both of which produced far less corrosive byproducts than today's chemical processes. When medieval iron was exposed to the open air, it interacted with an atmosphere much cleaner and more stable than ours, slowing oxidation dramatically. This helps explain why iron recovered from medieval rooftops, gates, and tools often remains structurally sound after centuries of exposure.